Hello, my name is Lawrence. I'm standing here in my poor man's stage, PMS. Today we will talk about Betelgeuse. Betelgeuse is a star in the constellation of Orion. This star Betelgeuse has dimmed a lot lately. You may have heard about it on the news. By now its light is more than twice as weak as it was before. This weakening means that the internal oven, or we call that the core, inside the star has become weaker. This oven normally is very hot and active, and what is very important to understand here is that this incredibly hot and violent activity pushes the outer shells of the star outwards. This means that it avoids that the star collapses onto itself. But when the core becomes very inactive, then it's possible that it collapses under its own weight because the core is not able to push outwards. It is inactive. And well, when that happens, when the core becomes inactive, then the outer layers of the star can collapse onto the core. And when that happens, the star will react. It will explode in a supernova. That means that the star will become very bright for a moment, and after that there will be a remnant, which will be either a neutron star or a black hole. Is this star Betelgeuse going to explode soon? That would be a very good question to answer. And the answer is yes. But do not run to your backyard just yet, because soon in astrophysics means roughly within 100,000 years. And yes, that means it could explode tonight or right now. And if it explodes, we must ask ourselves a more urgent question. What we must ask ourselves is this supernova in our vicinity dangerous for us? And of course, what can we do to avoid these dangers to happen, if any? What we do know is that biologic activity on this planet has existed for billions of years, and it still exists. And it's obvious not the first time a star in our vicinity goes supernova. And the bio did not disappear during 4 billion of years of supernovas. But we make this video because there are some indications that there might be a danger. And the danger lies in the sun. Yes, our sun that rises every morning in the east and sets in the evening. So, what is it that can go wrong with our sun? Well, we know that when a star goes supernova, it will release 99% of its binding energy in the form of neutrinos. Neutrino radiation will take less than 30 seconds to emit 10 to the 46th joule of energy in neutrinos. And that's much energy. Fortunately, neutrinos are particles that hardly interact with normal matter. They go right through us and we don't notice. Most neutrinos go right through the Earth and right through the sun. We are able to measure those neutrinos indirectly because once in a while they do interact with matter. And if you want to measure a neutrino, what you need is a lot of matter, like a huge water basin and photocells. This way we can measure that our sun produces a continuous neutrino shower. But those solar neutrinos are of a relatively low energy type. Supernova neutrinos are high energy neutrinos, and for less than 30 seconds there are lots of them. I do not claim to know how those neutrinos will affect the core of the sun, but I do have some indications that they do. In order to find a correlation between supernovas and solar activity, we would need historical data on the radiation of the sun. And guess what? We have that data. When the sun radiates harder, then it will convert more nitrogen 14 into carbon 14 up in the high atmosphere. This means that the concentration of C14 in the atmosphere increases when the sun shines harder. And this historical C14 concentration can be found in deep ice layers on the South Pole. These measurements were done, and up here you can see the historical graph of C14 concentration in the atmosphere. And this C14 concentration graph is then an indirect graph of historical solar activity strength. On the other display, we show a timeline of historical supernovas. These were nearly all supernovas that were observed with the naked eye. Some were confirmed supernovas from more than 1,000 years ago, from China and all kinds of places. All those visible supernovae were relatively close by. The furthest one was only about 35,000 light years away, and that's still further than the center of the Milky Way, because that one is about 25,000 light years away. The closest supernova that has been observed in history was only at a 6,500 light years distance from our planet. The radiation intensity from a supernova obeys the inverse squared law. This means that the intensity of the radiation dilutes with the squared distance. So let us grab the supernova force influence on the sun for each supernova as a function of its distance. Of course, all supernovas are different, and the force of each one of them does not only depend on its distance, but distance is by far the most important factor. So we can use distance as a measure. The initial radiation intensity is also a function of the initial mass of the star. More initial mass means more radiation during the supernova. The radiation also depends on the supernova mechanism. Betelgeuse supernova will probably be a type 2 mechanism. And that means that Betelgeuse at one point will have burned up all the inner core fuel at the star, inner core. This means that the true inner core of the star, there is nearly only iron left. Iron is like the ashes of the fusion reaction. Iron will not fuse or burn any further. The fusion reaction that is still present there in those layers cannot sustain the inward pressure, and the Betelgeuse iron core will collapse, and the outer layers of the star will collapse on top of that. And this collapse generates so much energy that Betelgeuse will rebound and explode in a supernova. And now back to the question. Why do I think that close-by supernovas affect the sun? Well, when we merge the graphs on the left and the right, we can see the supernova moments in time in red together with the distance of the supernovas expressed as the peak heights. This information in the graph also shows the solar activity chronologically. Now, solar activity variation depends on many factors, and the Sun has various cycles that interfere with each other. Supernovas would be just one more factor that may affect the long-term stability of the Sun. In the graph, we can observe 3 supernova clusters in the last 2000 years. Variations in the solar activity go very slow. As you may know, there is a well-known 11-year cycle in the solar activity, and there are more cycles. Energy generated inside the solar core will take years to reach the surface. Therefore, with a 100-year average filter, those fast variations can be filtered. In this way, trends become visible. So this yields the green trend line. It seems as if supernova activity affects the equilibrium of the solar core, because you can follow the arrows. Neutrinos, we know, interfere with matter through the weak forces, and those weak forces also play a crucial role in the fusion reactions inside the cores of stars. Therefore, high-energy neutrinos' presence could play a role in the activity of the solar core. During the 20-second supernova high-energy neutrino shower, the fusion activity may suddenly increase, and this will deplete hydrogen in the core and increase the core temperature. Then the pp chain to CNO cycle ratio will unbalance, and this will unbalance the solar convection. Then after some time the core will grow colder again, and it will grow even colder than it already was, because now there is lack of fuel. Say Betelgeuse goes supernova in 2020. Then let's place Betelgeuse inside the graph that we have together with the other supernovas. Remember that the neutrino intensity follows the inverse squared law. So Betelgeuse is at 600 light years, well, let's say 700 light years away. Okay, so if we put it in there, like this, then Betelgeuse will dwarf all the other supernovas in relative strength. The relative strength is because of this relative close distance of Betelgeuse from the Sun. So the effect of this supernova will then also be much, much stronger than all the other historical supernovas that were visible in the last 2000 years. Yes, and what will that mean for the Sun? Okay, this may go like this. So Betelgeuse goes supernova, it explodes. Then in the first 10 to 20 seconds, a gigantic neutrino shower will come out of the dying star. Here this is displayed as an expanding glass orb. You see, it comes first. The neutrinos will rush towards us and to the Sun and reach the core. See that? The core is a big, incredibly dense plasma mass. The neutrinos will interact with the plasma through the weak interaction, and therefore the core fusion will accelerate. You see, it becomes whiter and it becomes bigger, so it becomes stronger. Well, the core will heat up and the core will become larger. This will disequilibrate the core by depleting fuel from the core, right? Because it's burning more than normal. Therefore, after a while, the core fusion will decelerate because there is less fuel and the Sun is not made for that. And then the core will decelerate, cool down again, finding less fuel, and it will even then cool down even more because the fuel that was there for the normal functioning is now not there anymore. So through convection, the outer surface will respond retarded, but we can monitor the activity of the core through solar neutrinos, and we know what is coming. The sun will dim. That happens later on. Late after the core becomes colder, then the outer layers will dim. Who knows how much? And then the core will restart and get back to normal. But of course, we may enter a glacial period. Now we can understand why Betelgeuse is dimming so much, seemingly out of the blue. This may happen because of supernova 1006. SN supernova 1006 exploded about 6000 BC. Call it T is 0. And the neutrinos and the light from supernova 1006 reached the sun in 1006. At T about 7200 years later, because it's sitting at 7200 light years from us. You can see that happening in this animation here. Now, presume Betelgeuse is sitting at 600 light years. Well, the SN 1006 supernova neutrinos reach Betelgeuse sometimes later. Well, about 413 years later. This is 3D Pythagoras made visible. Then Betelgeuse dims because of the supernova neutrinos from SN 1006, as I explained before, and the dim light come towards us. That will take another 600 years because it's sitting at 600 years from us. That's what we presumed. And then that will reach us in 1006 plus 413 plus 600 is 2019. It will take a while between the neutrino reach Betelgeuse core and the dimming of the outer layer, say 5 years, and that means that Betelgeuse is sitting at approximately 605, give or take 10 light years from us. If Betelgeuse does go supernova, then that may have been induced by supernova 1006. Well, that was it for today. I can see the effect of supernovas in the C14 curves. However, one thing is correlation and another thing is causation. So, who knows, I might be wrong about this. I'm just seeing ghosts. But if not, then nothing can be done to avoid this from happening. Except maybe pray to God. Who knows? He can diminish the effects of natural disasters. Bye. Oh, wait a second, I forget something. Yeah. If you have a piece of plutonium, enriched plutonium or uranium lying on your shelf or in your closet or in a silo somewhere, some slightly subcritical mass so that it just not explodes, safe. Not sure why you would have that though, but if you have that, well, during the supernova it may just explode out of the blue, on the shelf, in the silo, wherever. Who knows?